Our last section in this chapter will be vectors. First, you need to know the difference between a scalar quantity and a vector quantity. Scalars have only magnitude or a size. An example would be 55 miles per hour, whereas a vector quantity has both magnitude and direction, and this is the key to the difference. Vectors have direction. So if I took that same example of 55 miles per hour, and now I put a direction on it and indicated north, then it turns into a vector quantity. And I've listed some examples of scalar quantities: distance, speed, mass, and time, and vector quantities: displacement, velocity, acceleration, and force. These are some of the ones that we'll be starting out with this year. Since a vector has direction, when you draw a vector, you simply draw an arrow. It's got a tail and it has a head. The head is the part that looks like an arrow and it points in the direction that you're indicating. When we look at a symbol for a vector, you can use any variable. I just picked a variable of an A in this case to indicate that the number you're going to look for is a vector quantity. You would simply draw a small arrow on top of that variable. This arrow on the variable is always the same regardless of the direction of the actual vector. And we're going to practice with some of these. The easiest way to practice is by example. So we're going to start out adding parallel vectors together. We have a new vocabulary term. The vector sum is called the resultant, so you'll need to know what that means. And it's going to be a sum just like a normal sum when you add two numbers together, except now with vectors, we're going to indicate a direction in our answer. Now in class, we're going to have a number line on the front board. Anything that's drawn to the right is going to be a positive number, and anything drawn to the left is going to be a negative number. This will be our coordinate system. So for example, my first vector, vector A, I'm going to say that it is 1, 2, 3, 4 segments, and it points to the right. So vector A would be equal to a positive 4. When we look at vector B, it is 1, 2 segments in the positive direction. So we would say that vector B is equal to positive 2. Now when we add these together, we're just going to add vector A and vector B together. And I know that easily in your head you can say 4 plus 2 is 6. However, if I just answered the number 6 by itself, that doesn't tell me which direction the resultant vector would be facing. So it's really important that I include a plus sign anytime I'm talking about a vector quantity, because a positive and a negative are ways to indicate a direction. So by saying plus 6, that lets me know that when I add these two vectors together, I'm going to get 1, 2, 3, 4, 5, 6 segments in the positive direction as my answer. Let's do one more together. I kept vector A the same. It is still positive direction and a length of 4. But vector B this time, I switched its direction. Notice the arrowhead points in the opposite way. So vector B is now a negative 2. And then also notice that the notation on the variable itself still points to the right. Remember that this little arrow on top of the variables doesn't necessarily tell you which direction a vector is facing. It's only to let you know that you should be looking for a direction as part of your answer. So in this case, now I'm going to add vectors A and B together. You would simply say positive 4, and then we're subtracting a negative 2, so that leaves us with an answer of positive 2. So remember, it's not just 2. I can't have the number by itself. I need to say which direction it is. And by using this little plus sign right here, that lets me know that my final answer is actually pointing in the positive direction. So now go ahead and pause the video and try one by yourself. You should have gotten an answer of negative 1. Next, we just have some general properties about vectors. Any vector can be moved parallel to itself in a diagram. What this means is I can move the vector around, but I cannot rotate it. We can also add vectors in any order, and then to subtract a vector, you're adding its opposite. So remember, a negative sign for a vector simply indicates the opposite direction. And then if you multiply or divide vectors by scalar quantities, you're still going to get a vector quantity as your answer, which means you want to look for a direction in your final answer. Remember, this first rule was really important. Any vector can be moved parallel to itself, but you cannot rotate it. That's very important, so you may want to write that down. You cannot rotate a vector. So that means on this vector that I drew, I can slide it anywhere I want to, but it's always going to point in that same direction. I just cannot spin it around and make it point in a different way. Next, we're going to look at how you can add vectors together that are not parallel to each other. There are two different methods. I would advise the head to tail method. I think it's a little bit easier and more common, and if you ever have more than two vectors, that would be the one you want to use. However, I'm going to show you both of them and let you decide for yourself which one works best for you. So let's start out. This time I've got two vectors, one that points like this, and I'm going to add my second vector, which is pointing upwards. Notice that they are lined up head to tail. It's called the head to tail method, or you might see tip to tail. What that means is I'm going to take the head of one vector or the tip of one vector and line it up to the tail of the next one and continue on that path. Now, for our resultant, remember the resultant is the answer to the vector sum. When I add these together, it is always going to point from start, and it's going to end up at the final spot. So in this case, it would look like that. I started down here drawing, and I finished my vectors up here in this corner. And I put an R with an arrow for resultant. Now if we look at completing the parallelogram method, I take those same two vectors right underneath. I have the blue one pointing, let's say east, and the green one pointing north. I just line them up differently where everything is tail to tail. All of the vectors start with their tails touching each other. And to find the resultant, I would simply do what the method says and complete the parallelogram. So I draw a parallel vector next to the blue one, and then I draw a parallel line next to the green vector. And my resultant would then point, starting at the same tip with all of them, and it would point to the opposite corner. So now, if you notice, the two resultants, they point in the same direction for either method, so you get the same answer either way. I'm going to do one more for you. So I've color-coded again. I've got my blue vector pointing west, and then my green vector pointing kind of northwest. And I line them up differently. For this first method, I line them up tip to tail or head to tail, and my resultant would point from start to finish. So I started drawing my vectors here, and they finish in that direction. Or I could complete the parallelogram. So I would draw a line parallel to the blue vector and one parallel to the green vector, and where those cross each other is where my resultant would point. So I start with all the tails lined up and I point to the opposite corner of that parallelogram. And again, notice that the two R's, the resultant, the answer, and both of those are pointing in the same direction. So pause the video and you try the last one. I hope you were able to do that one and you got it correct. Again, notice that your answer is the same for either method, so it's really up to you which one you prefer. And however, remember that the tip to tail method is definitely a good one, because we're going to see in the next example that if you have more than two vectors, you'll need to line all of them up tip to tail or head to tail. So now let's see how we can combine more than one vector. So I'm going to take the example and I'm going to line them all up tip to tail in order. So if you noticed, I drew vectors and I said 4 to the east, 1 step south, 2 to the west, and then 5 south again. When you're drawing vectors like this, you want them to be as in proportion as possible to each other. So for example, this one that went 2 back to the west, it should end up at about the halfway mark of my first vector that was 4 in length. From this point, when I draw my resultant, since I've lined them all up head to tail, I started at this position and I finished down here, and that's where I'm going to draw my resultant vector from start to finish. So it's going to look something like this. We're going to do a lab where you're going to practice drawing a map and draw your vectors in steps such as these. And then eventually, I'm also going to ask you how to calculate that resultant length for that vector. So if we practiced and looked at that now, I can go ahead and break down my picture into a right triangle. So if you notice, if I take this 5 vector and extend it all the way up, I've created a right triangle. So I'm going to redraw that triangle over here. My resultant looks something like this. Now that we have a right angle, I can look at my original picture and look at just this length, and you should come up with a length of 2. Okay, because remember originally it was 4 and then we came back 2 steps, so that would be 2 for that one. For this long length of the triangle, I would take my vector that had a magnitude of 1 and my vector that had a magnitude of 6. Those were in the same direction, so I would add those together and get 6 for that part of the triangle. At this point, hopefully you recognize that we're finding the hypotenuse of a right triangle, and you can simply use the Pythagorean theorem. So I could plug those numbers in, and then notice when I write my final answer, I'm going to use the vector notation, and the square root of 40 is about 6.3. And then I would include a direction, and in this case, my resultant vector pointed somewhat southeast. So I would include that direction as part of my final answer. So this leads us to vector addition in 2 dimensions. In the beginning, we're just going to do vectors that are at right angles to each other if they're not parallel, so you'll easily be able to see an angle, and then you should be able to tell from this picture that our resultant points in that direction. And I know you're probably more familiar with a squared plus b squared equals c squared, but we're going to write it in terms of the physics variables that we're looking at. Our x variable is the horizontal one, which is similar to the x-axis of a graph, and then the y variable is vertical. Our resultant is always going to be the hypotenuse. So it should be easily recognizable. The resultant, is always the hypotenuse. Next, we have the components. So if, for example, I were to give you a number on the hypotenuse and told you what the resultant is, and I gave you an angle, by knowing just those 2 numbers, the hypotenuse or the resultant and the angle, I would be able to find out what the x and y legs are equal to of the triangle. And when we say the x and y legs, those are called components. So that's what we're referring to, the horizontal and the vertical component of our right triangle. So if you have not had sine, cosine, and tangent before, I made you a little chart over here in this little section. It's SOHCAHTOA, just a little abbreviation. Whenever you have the sine of something, I'm just going to put an equal sign right here. To find the sine, I would take the opposite leg over the hypotenuse, so I'm going to put a little division there. Cosine would be equal to adjacent over hypotenuse, and tangent would be equal to opposite over adjacent. And then from those, I can rearrange and come up with the formulas that you see over on the right. We could also use these to find the angle. So if, for example, you're given 2 legs of a triangle, usually it would be the x and the y legs for our components. I could find the angle by using the inverse tangent. And we're going to do some examples of these in class, so don't worry if it seems a little bit new to you. I just wanted you to have the formulas before you come to class. You'll notice that the next section of your notes, there are 5 example problems. Please bring those with you, and we're going to go over them together in class, so it'll give you a chance to ask questions and you can see how to apply these formulas.